F10-5. Determine the moment of inertia of the beam's cross-sectional area about the centroidal x and y axes. So this beam, we could set it up as a complicated piecewise integral, or we could use the principle of superposition and break this beam up into a group of rectangles. Now it might be tempted to say one rectangle vertical, one rectangle horizontal, but that would double count this section in the middle where they intersect. There are a few other ways you could cut this up. The way that I am going to work this is by cutting up this vertical piece as one rectangle and these two pieces as other rectangles. One advantage of this is that these two pieces are symmetric, which means that the moment of inertia of one should equal the moment of inertia of the other. So I only have to calculate once and multiply by 2. So first, let's start with the moment of inertia about the x-axis. So first, the vertical. The formula for moment of inertia is 1/12 bh cubed. B is the length along that axis. So for this rectangle, it's this 50 millimeters right here. And h is the length in the other direction. So h is the length in the y-axis in this case, which is 200 millimeters plus 50 plus 200, or 450 millimeters total. So 1/12 times 50 millimeters times 450 millimeters cubed gives 3.797 times 10 to the 8th millimeters to the 4th power. Calculating the moment of inertia of one of these rectangles, we say that this one has a base of 150 millimeters and a height of 50 millimeters. So 1/12 times 150 times 50 cubed is, and I converted this so that they would have the same exponent, 0.016 times 10 to the 8th millimeters to the 4th power. So to find the total moment of inertia, we take the moment of inertia of the vertical piece plus 2 times the moment of inertia of each of the horizontal pieces, add them together, and we get 3.829 times 10 to the 8th millimeters to the 4th power. Now, one thing I would like you to notice is that even though the horizontal component and the vertical components are in area roughly equal, not exactly, but roughly, it's this vertical beam contributes far more to the moment of inertia than the horizontal section. Part B, what is the moment of inertia about the y-axis? Now, if I wanted to make this problem easy, I would change what pieces I use. I would switch to using this piece along the x-axis and then 2 wings here and here. But for pedagogical purposes, I am going to keep the same sections as before, 1 vertical piece and 2 horizontal pieces. Now the vertical piece is, I can still use the 1/12 bh cubed. It is still a rectangle, we're still going through the centroid of the rectangle, we just have to switch what is base and what is height. In this case, base is the length along the y-axis, so base is the 450 millimeters, and height is the length along the x-axis now, is that 50 millimeters, to get a total of 0.469 times 10 to the 7th millimeters to the 4th power. Now for this chunk right here, this horizontal piece, I have to be careful. I can find its moment of inertia about its centroid using 1/12 bh cubed. But the centroid of this rectangle does not go through the y-axis, so I also need to figure out how far away the centroid is from the y-axis. So first things first, what is the centroid about the center? Well, this time base is this 50 millimeters, and height is 150 millimeters. So 1/12 base times height cubed gives 1.406 times 10 to the 7th millimeters to the 4th power. And again, that is the moment of inertia about the parallel y-axis. To get the moment of inertia about the actual y-axis, I take the moment of inertia about the centroid y-axis plus the area of that section times how far the centroid axis and the y-axis are separated. So this part was what we just calculated. The area is a simple base times height. And the distance, this centroid, or this section, is 150 millimeters across. So the centroid is 75 millimeters from the edge. Now from this part, we can see that this part is 50 millimeters across, so this edge is half of that, or 25 millimeters, away from the actual y-axis, which means the centroid is 75 millimeters plus 25 millimeters, or 100 millimeters, from the y-axis. So area times that 100 millimeters squared. Put all that together, and you get 8.906 times 10 to the 7th millimeters to the 4th power. From this, you can kind of see that that it being separated from the y-axis contributes far more than just its shape. Also keep in mind that there are two of them, so the total moment of inertia about the y-axis is equal to this times 2 plus this, which comes out to 1.828 times 10 to the 8th millimeters to the 4th power. Notice again that the contribution of the component along that axis is minuscule compared to the contribution of the piece perpendicular to that axis.